Hello everyone. So as a part of redox chemistry, today is very important topic, which is the redox titration. So redox titration actually falls under the potentiometric titrations. There are 6 types of potentiometric titration. Potentiometric titration means the titration where potentiometer is used. A potentiometer means 2 half cells are connected. One of the half cells is the indicator half cell, that means where the reaction is taking place, that is the system, and another one is the reference electrode, that means it may be normal hydrogen electrode, but practically in the market the reference electrodes available are generally saturated calomel electrode. The electrode potential of that electrode is actually 0.28, so that value has to be deducted from the overall electrode potential. So as I was talking about the potentiometric titrations, so there are 6 types of potentiometric titrations, out of which 4 are very important. So these 4 types of potentiometric titrations where the potentiometer is used are: number 1, acid-base titration; number 2, redox titration; number 3, precipitation titration; and number 4 is compostiometric titration. So all these 4 types of titrations you have got to do in your practical classes. So now our today's topic is redox titration. So in this regard, we have to recall the chemical equation, which I was talking about in my 4th lecture. In my 4th class, you have calculated the Kc value, that means the equilibrium constant value of this reaction where cerium 4 plus reacted with iron 2 plus to produce cerium 3 plus and iron 3 plus. So here 100 ml of 0.1 molar ferrous sulfate solution in the H2SO4 solution has been taken in the conical flask, and in the burette cerium sulfate CeSO4 whole twice solution has been taken in the burette whose strength is 0.1 molar, and which this solution is being added dropwise. So what will happen in the overall redox potential of the system if this is being added to this iron system? So the overall reaction would take place is this one. Here cerium 4 plus is the oxidant, iron 2 plus is the reductant, and they will produce the oxidant form. Cerium iron 3 plus will be the oxidant now, and cerium 3 plus would be the reductant now. So before going to the reaction, we have to know we have to have some idea about the standard electrode potential of the iron system as well as that of the cerium system. So the standard electrode potential of the iron system is 0.75 volt, while that of the cerium system is plus 1.45 volt. So let us take 100 ml of ferrous sulfate solution in the conical flask, and right now no cerium has been added. Okay, so the overall electrode potential is 0. Okay, because the half cell has not been created. Now if you add 1 milliliter of 0.1 mole of cerium 4 plus solution, then it will immediately oxidize 1 ml of iron 2 plus to produce 1 ml of iron 3 plus, and itself it will become cerium 3 plus. Okay, so since there is no cerium 4 plus remaining in the solution, so cerium system will have no contribution towards the overall electrode potential of the system. The overall electrode potential will be determined by the system where 2 oxidant and reductant form of the similar species would coexist, and this too is iron system, that of the iron system. So right now iron is 99 ml ferrous solution, and you have 1 ml of ferric solution in your system. Now use these 2 Nernst equations. Okay, so first, in the first part of this titration, you have to calculate the redox potential of the system by using this Nernst equation where iron system is used, and in the second phase you have to use this equation. Okay, so in this equation, the Nernst equation, E1, the redox potential of the system is E10, that is standard electrode potential of iron, plus 0.0591 by 1, that is the standard form, the equation number 6 of the Nernst equation, as I've said earlier, plus logarithm of the concentration of the oxidant form by the reductant form. Okay, here we are using plus sign, that means oxidant will be in the numerator and reductant will be in the denominator. You can also use the negative sign here also. In that case, the reductant will be in the numerator and the oxidant will be in the denominator. But according to the IUPAC convention, you better I would like to suggest you to use this equation. Okay, this convention. Now you just take a calculator or pen or paper and try to put these values as being displayed here in this slide, and try to tally the overall electrode potential by calculating yourself by pausing the video time to time. Okay, first of all, 1 ml of ferric solution was added, and then after that 10 ml added, then 20 ml. So whatever be the amount of ferric solution, it will immediately be converted into I'm sorry, whatever be the concentration of cerium 4 plus, it will immediately be converted into cerium 3 plus by converting iron 2 plus into the equal amount of iron 3 plus. Equal amount of iron 3 plus means if you add 10 ml of cerium solution, cerium 4 plus solution, then 10 ml of ferric solution will be produced. If you add 90 ml of cerium 4 plus solution, then immediately 90 ml of ferric solution will be produced. Okay, and this 90 ml of cerium 4 plus will itself convert into 90 ml of cerium 3 plus solution. So try to put these values. Okay, here suppose here in the first case 1 by 90. Okay, here 1 divided by 90. So try to find out the value of E1. Here suppose 50 ml. This is very interesting. 50 ml iron, 50 ml iron 2 plus, 50 ml iron 3 plus. So 50 by 50 means 1. That means this term log 1 means 0. So it will be E1 will be equal to E1 0. And look here in this column, it is plus 0.75. That is, it is equal to that of the standard electrode potential of the iron system, isn't it? So this is very interesting. Now, after having crossed the half mark, here in 90 ml, you will calculate and tally also with this value, which will be 0.81 volt. Okay, now look here, the color has been changed from blue to pink. That means at this point, okay, at this point I was using to add the cerium 4 plus solution by 10 ml. Okay, 0 to 10 ml, 10 to 20, this way up to 90 ml. But now I'll be adding 1 ml. Okay, cerium 4 plus will be added by 1 ml, because here you will find by your calculation that the increase in the electrode potential value will be little bit in the higher rate than the previous ones. Okay, you find that 80 to 90, 80 ml to 90 ml, the change is 0.79 to 0.81, isn't it? So 0.02, the change is 0.02. Now in the next slide you find 93, 94, 95, here 99. You look, just 9 ml has been added, and what is the change? 0.81 to 0.87, that is 0.06. So in the previous slide, for 10 ml addition, the increase was 0.02. In the next slide, for further 9 ml addition, just the change is 0.06. 0.81 to 0.87. Okay, so 0.06 volt increase. So that is why here this addition amount has been made into parts of 1 milliliter, and this after that, after 99 ml, the addition has been divided into the part of 0.1 ml. So the part from 10 ml to 1 ml to 0.1 ml. Okay, gradually the part has been just what I say divided into many additions, so that the exact amount of change is reflected properly. Okay, you find here from 99 to 99.9, 99.8, then 99.9. Here So since this amount of addition has been distributed into smaller parts, so this change in the value of E1 or overall E is well reflected, or can be well detected, that at what speed it is going to be it is increasing. Okay, now the point is that if you add total 100 ml of cerium 4 plus solution, at that point the equivalence point is reached. So what will happen at that point? What will happen is the concentration of ferric ion and cerium 3 plus ion would be equal, and the concentration of Fe2 plus ion and cerium 4 plus ion would be equal, and the corresponding E, overall E0 value would be calculated by calculating E1 plus E2 by 2 by using this equation. Now E1 value at 25 degrees Celsius for iron is 0.75, and E1 value at 25 degrees Celsius for cerium is 1.45. So E1 plus E2 by 2 is actually 2.2 by 2, that is 1.1 volt. Okay, so this is the point where at the equivalence point what would be the value of overall electrode potential of the system. Now after adding some excess of cerium, what will happen? Here also you can pause the video and put the values, but you have to put the values in this equation. Which equation? No, this equation. Okay, so in the place of E20 you have to put 1.45 plus 1.45. okay, and here in the concentration of cerium 4 plus and here in the concentration of cerium 3 plus, you put the proper values and tally the result, tally your result with these results what are being given here in this slide. Okay, so what is the overall conclusion? That at equivalence point the change in the redox potential of the system would be drastic. Okay, so we have to put this graphically. Before that we have to elaborate how this equation was obtained. Actually the exact equation was this one. Okay, species 1 which has stoichiometry A, species B, species 2 which has stoichiometry B. So it is playing the role of an oxidant. It is oxidizing species B, species 2, and it is becoming then species 1 reductant. That means cerium 4 plus reducing iron 2 plus, oxidizing iron 2 plus to become cerium 3 plus. On the other hand, here iron 2 plus is reacting with cerium 4 plus to become iron 3 plus. So here iron 3 plus is the oxidant, cerium 3 plus is the reductant. So species 1 is cerium, species 2 is iron. Now here in the left hand side, species 1 is actually in the oxidant form, species 2 is in the reductant form. On the other hand, in the right hand side, after the reaction, species 1 is playing the role of a reductant and species 2 is playing the role of an oxidant. Okay, so if there is some stoichiometry, then the electrode potential at the equivalence point would be calculated by using this equation. Actually, if you apply this equation in the previous system, their stoichiometries, what had been their stoichiometries? A was 1, B was also 1. So 1 into E10 plus 1 into E20 divided by 1 plus 1. That means the equation E10 plus E20 by 2. Okay, now finally the graphical presentation. Okay, so this is the graphical presentation of the of the change in electrode potential with respect to the volume of cerium 4 plus added into the iron solution. Okay, in the x-axis. So here you look that the value of the E electrode potential is gradually increasing. Here some rapid increase taking place. So by observing this rapid increase, we can easily detect the equivalence point of the system, and you find that the electrode potential at the equivalence point is 1.10 volt. Okay, now sometimes if you feel it is difficult to detect this equivalent point, then you can also go for the differential curve. At that case, dE dV is plotted against, here only E is plotted against V, but if you feel it to be difficult to plot this graph and to detect the equivalence point, then you can go for the differential curve. How you would calculate the dE/dV value? That means with the change in volume, the change in E. Suppose you change from 80 ml to 90 ml. So what is the dV? 90 minus 80 is the dV value. So 10. dV is 10. 90 minus 80 equal to 10. What is the change in E? E was changing from 0.79 to 0.81. So what is the overall change? What is the difference in its change? The difference is 0.81 minus 0.79. That means 0.02. So what is the dE/dV value? dE/dV value is actually delta E by delta V value is 0.02 divided by 10. Okay. So that value is 2 into 10 to the power minus 3. So these values are plotted in the y-axis and V as usual in the x-axis. In that case, the graphical presentation or graphical plot would be like this. Look the movement of the cursor. It is going. At the equivalent point, you will get a peak like this. Then it will be again a flat curve. Okay, I repeat. It is going as usual. Okay, here at this equivalent point, you get a peak. Then again the curve is flattened. Okay, so here dE/dV or delta E by delta V is plotted in the y-axis against the volume of cerium added. Okay, so that's all for today regarding the redox titration. Thank you.